Welcome everyone to day 11. Your homework will be packet page 7. Here's your homework answers from last night. So you can, as usual, pause it on here, check your answers. If you are good with everything, you can fast forward to the start of the lesson, or whatever ones you're missing, you can just fast forward to me going over just those ones. You can skip over any ones that you were good with. So again, pause here and check each of those. So do your derivative, x to the 1/2, square it and add 1. So we get x plus 1 underneath. You did a u substitution. Change your bounds to your antiderivative and fill in. Got your exact value there on the left to 3 decimal places on the right. Your derivative of natural log is derivative inside over the inside. So you had secant tan over secant. The secants wipe out, you get tan. Square that and add 1, you get tan squared plus 1. Well, that's a Pythagorean identity. It's just secant squared. So that goes under our radical. Take the square root of it, you just get secant. Secant's antiderivative is natural log absolute value, secant x plus tan x. Fill in your values, you got your exact value there, the natural log square root of 2 plus 1. Now in 3, starting with 3, you could punch these in on the calculator. In number 3, when you do your derivative, square it, and add 1, you end up getting the same setup as question 1, and then you're just doing it on the calculator. In 4, your derivative is cos, square it, and add 1. Note cos squared plus 1 is not sine squared. We got that from 0 to pi. Make sure you're in radian mode. Plug it in 3 decimal places. In 5, derivative of e to the x, just e to the x, square it, add 1, put it under your radical with the interval, and you got your 3 decimal places there. There's 6 and 7. 6 was pretty straightforward, hopefully 7. You got to remember to do chain rule, so multiply by the negative 2x after. Now any of these you can always just put in parentheses squared and then plus 1 if you are going to be doing it on the calculator. No need to really neaten it up inside. Derivative of arctan is 1 over 1 plus x squared. You could really just stick that in parentheses, squared plus 1 under the radical. You got your interval, got your 3 decimal places. In 9, just keep the 2 out front. Derivative of 3y is 3 over 3y. The 3 is divide out, so we just get 2 over y. Square it, add 1, stick it under your radical. And then similar idea with this one. Take your derivative, square it, plus 1, put it under the radical to 3 decimal places. Now the review ones, so in our chart, we were doing when x is equal to -1 for f. So at -1, the y value is 1 and the slope was 3. So you got y minus 1 equals 3 times x plus 1. In 2, you had to do your product rule out. Your derivative of f at 1 was 0.5. Regular g at 1 was 2. Regular f at 1 was 4. Derivative of g at 1 was -1. Multiply and add those, you get -3. 3 was a similar idea, but with quotient rule in order to find your derivative of m, and we were also evaluating at 3 as opposed to 1. So at the end there, I switched the 1.44 to fraction form just to neaten it up and get it an exact fraction. Remember, you could also divide it and do menu number approximate to fraction for that as well. 4, you got a chain rule, so f prime, keep the inside the same, then times g prime of x. So at 0, g is just 3, so you're really doing f prime of 3 to get -3. G prime of 0 is -2, multiply them together. And your chain rule in 5, G prime, keep the inside the same, times the derivative of the inside, which was 2x. Put the -1 in for x, you'll get -2 at the end. The -1 squared gives you 1, and g prime of 1 was just -1, so in the end we'll get 2. All right, today is the last new topic in the unit. We've got surface area of solids of revolution. So say you took y equals 2 radical x on 0, 3 and spun it around the x-axis. And then we sliced it all up. Well, what we're going to try and do is find the surface area today. That strip that is shown there is basically the thing that we would want to find the area of. Over on the right is essentially what we can think of that shape as being. It's called a frustum. It's essentially a cone that has had the top chopped off. So imagine you have a cone, you chop off the top little cone, and what you're left with. Kind of looks like a stopper or something like that. So you have two radii there, the radii, the bottom circle, the radii, the top circle. We're calling R1 and R2. You've got the slant, which we'll call S, and then you've got the H. Well, the slant in that, the S, is really our arc length. And we did that on the homework yesterday. So the arc length is really just the S. Well, as the number of slices goes to infinity, these are going to get infinitely thin. As they get infinitely thin, the lengths of R1 and R2 will approach each other. So we can then modify the formula to say, well, because R1 and R2 are going to approach each other, that's like we're going to have 2 times our radius in there. Well, if we neaten that up then, our lateral surface area of this, which is our surface area of our strips that we're working with, is really just 2 pi times the radius times the arc length. Well, we really know how to find arc length from the previous day. That's just our derivative squared plus 1 under the radical. So the new thing for today is we'll just have a 2 pi and times some radius. So let's look at that example, the 2 radical x on 0 to 3. So we need to do 2 pi times the radius times the arc length. When we are working with these, a good thing to keep in mind is in general what y and x are defined as. This is y, it's a vertical coming from the x-axis, and this is x. So our radius here would just be this length, which is just a y, which is why in this step we have 2 pi times y times the arc length. Well, because we're slicing vertically, and because our function is in terms of x's, it might be easiest to do everything with x's. We'll see in the next one that really we can do arc length. Like we saw, we could do arc length in terms of x or y. You can also do surface area in terms of x or y. It doesn't matter. So, because our original equation was in terms of x's, instead of having y there, let's put in what y is. And that's where this 2 radical x is coming from. Then for our arc length, we would just have to do our derivative squared plus 1. So let's do that so that we could add it in. So we know this is going to be the integral. I'm going to put the 2 pi out in front here from 0 to 3. Actually, we can put 4 pi out in front because we had the 2 there. We're going to have a square root of x times some square root, and we'll figure out what that is. So our derivative just a reminder, our original was y equals square root of x. Our derivative, multiply the 1/2 out front and you get 1. We'll have times x to the negative 1/2, and then derivative of the inside is just 1. So if we square that and add 1, this is squared will give us x to the negative 1, and then we'll have our plus 1. Or in other words, that's really 1 over x plus 1. So let's put that inside here. Throw our dx on the end. So if this was one that you could solve in the calculator, you would just throw it in and see what you get. But we're going to show you how we can do this one algebraically. Well, when you have radicals, you can multiply the parts inside the radical together. So that x can distribute through the radical. X times 1 over x will give us 1. X times 1 is just x. And now we can just do a little u substitution for this. So du will just equal dx. We'll have to change our bounds. If we put 0 in for x in the u, we'll get 1. If we put 3 in, we'll get 4. And this will now just be u to the 1/2 du. Our antiderivative, we'll have u to the 3/2 with a 2/3 out front. And we're going to go from 1 to 4. Well, this is really 8 pi over 3 out front. 4 to the 3/2, square root of 4 is 2, 2 to the 3rd is 8, and then 1 raised to anything is 1. So this will be 7 times 8/3, which 8/3 pi, sorry, so this will be 56 pi over 3 for our surface area of the solid when that is spun around the x-axis. So again, we can do these in terms of x or y. It doesn't matter. Just make sure you have consistency with your radius and your arc length setup when you're doing that. And then if you're going to do it in terms of y's, like the second one there, make sure your integral bounds are y values as opposed to x values. So just to give you an example of this, we're going to do the exact same problem that we just did and do it in terms of y's. Well, our original equation we had was y equals 2 squared root of x. And we were going on the interval from 0 to 3. Well, we'll have our 2 pi. If we're doing this on y's, we need our bounds to be y values. So if we put in 0 to our original equation, we'll get y equals 0. And if we put in 3, we'll get 2 squared root of 3. Again, keep in mind, we always consider that x and that y. So if we drew in our radius here, that's just a y. So in this case, we can just leave it as y because we're going to do it as dy. For our arc length, we need to get our function in terms of y. So in other words, x by itself. So we can divide the 2 over and then square both sides, and we'll get 1/4 y is equal to, 1/4 y squared is equal to x. So we'll take our derivative. We'll just call it x prime. That'll be 2 times a fourth will give us 1/2 y. If we square that and add 1, we'll get 1/4 y squared plus 1. And that's what will go under our radical. And we'll stick our dy at the end. Well, this sets up nicely for a u substitution. The u would be our 1/4 y squared plus 1. Du, 2 times a fourth will give us 1/2 y dy. And we only had a leftover y, so we'd have to correct by multiplying by 2. So we've got the 2 pi that was out front and the 2 from our u substitution. So we're going to have 4 pi. We're going to have u to the 1/2 du. And we've got to change our bounds. So we'll put 0 in the 2 radical 3 and for y here to see what we get back for u. 0 squared is 0, times a fourth is 0, plus 1 is 1. 2 squared of 3 is really 4 times, or when we square it, is really 4 times 3, which is 12, times a fourth, which is 3, plus 1 is 4. And you may recognize that right now this is the same thing we had after we did u substitution for the x's. So we'll have 4 pi. We're going to have u to the 3/2 with a 2/3 out front. and we're going to go from 1 to 4. So this is 8 pi over 3 again. 4 to the 3 halves again is 8, minus the 1. So this will give us 56 pi over 3 for our surface area. So this just shows you can do it in terms of x or in terms of y, and you'll get the same answer. Now, sometimes depending on what your original equation is, it might be easier to do one as opposed to the other. All right, the purple there is the x and y axis. And we're going to look at cos x plus 2. So that's the cos graph shifted up 2. And that's that blue function on the right. We're going to spin it around x equals -1, which is the green dotted line. And then we want to find the surface area. We've got one of those strips that we're finding the surface area of and then adding up there in red. So our basic setup, again, is we're going to do 2 pi with an integral and then a radius times the arc length. Because this is in terms of x's, maybe we'll just stick with x's. So I have 2 pi, our integral. They told us we're going from 0 to pi over 2. So let's look at our radius. Our radius would be this length right here. But let's remember our basic idea is that that's always a y and that's always an x. Well, within that radius that I drew in, we have one of those things. The part from here to here, the part coming out right from the y-axis is our x. And then this is 1 extra. So our radius would just be x plus 1. We'll have a square root for our arc length and dx. We can figure out what that square root will be off to the side. So our derivative, dy over dx, is just negative sine x. When we square it and add 1, we're going to get sine squared x plus 1. Again, keep in mind that's not cos squared x. Cos squared would be 1 minus sine squared x. And this particular one, we do not have methods of how to find it algebraically, so go ahead and sub it in your calculator and keep it to 3 decimal places. We should be getting 22.076. And again, what that represents is our surface area of the 3-dimensional solid that is formed when we spin that region around x equals -1. One last one for this video. So we've got the graph of radical 2y going from 0 to 4.5 for the y's. So really for x's, if you sub those in, that would be x from 0 to 3. And then we're going about the line x equals 4. So this is our original function right here. So as it spins around, it kind of makes that an upside down funnel type shape. Or it looks like a volcano maybe. So we want to find the surface area. So again, we split it into those strips. We're going to have 2 pi. We are in terms of y's here, so we got 0 to 4.5 for our y's. And let's draw in our radius. The radius would be this length here. Well, if we keep in mind that this is always x and this is always y. If I were to draw in this here, together the green and the red, that length is 4. That squiggly red line we know is x, based on our definition of what an x is. So therefore, the radius we want, the green line, is just that 4 with the x taken away. So we're going to have 4 minus x, but we don't want any x's in there because we're doing it in terms of y. So we'll have 4 minus what x is really equal to. So 4 minus the radical 2y. We'll have something for our arc length, and then we'll have dy. So our derivative is going to be 1/2. 2y is really now raised to the negative 1/2 times the derivative of the inside, which is 2. So that's really just going to be 2y to the negative 1/2. If we square that, we're going to get 2y to the negative 1, and then add 1. And then we're going to have you just put this in your calculator again, see what you get to 3 decimal places. And you should have gotten for the surface area of that entire figure as it spun around, 77.930. And that's it for day 11 and our new material in this unit. We will review tomorrow in class, so hopefully you've been working on the review sheet and you also got the day 11 homework due tomorrow. Have a great rest of your day.